This curve is the trajectory of an object moving in 2 dimensions. Vector r is the position vector of that object. So we can imagine this object moving along the curve. Obviously, vector r is changing with time, so vector r is a function of time. Suppose that the object is at point P at time t, and at some small time delta t later it is at point Q. So this vector here we can write as r of t, because the object is at P at time t, and this vector here is r at time t plus delta t, because the object is at Q at time t plus delta t. Now the displacement vector is the vector joining points P to Q. So that vector represents the displacement of the object during a time interval of length delta t. So the length of this vector represents the distance travelled, and the direction gives the direction of motion. Of course, that's in the limit. As delta t goes to 0, the distance between points Q and P gets smaller and smaller, and the straight line distance is essentially the same as the distance along the curve. Now we can get the average velocity of the particle as it travelled from P to Q by getting the displacement vector PQ and dividing it by delta t, the time taken for the particle to go from points P to Q. Now just as a reminder, the displacement vector PQ is this vector here, r at time t plus delta t, minus vector r at time t. And to prove that, we can just add two vectors by the triangle law. If we take this vector here and add it to the displacement vector by the triangle law, we should get this vector here, and indeed we do. RT plus this will indeed give us this, because the RT's will cancel out when we add these two vectors together. Now if we take the limit as delta t goes to 0, then the average velocity vector, and this is a vector, becomes an instantaneous velocity vector at P. So I'm showing here the instantaneous velocity vector is tangential to the curve at P. Actually it would look more like this if it's tangential to the curve. Well, that's not even that. Well, this is my best impression of it. So this is the velocity vector, which we normally call v. So this is the instantaneous velocity vector of the object at the point P. The displacement PQ divided by delta t is just an average velocity. The average velocity would be in the same direction as PQ. It's just the displacement vector PQ scaled down by delta t. So the average velocity would be in the same direction. Same direction as PQ, but scaled down by this amount delta t. Now we could write the difference of the two vectors that are on top, the difference between r at t plus delta t and r at t, as delta r, d for difference. So it's the difference in those vectors, and delta r is of course a vector. It's vector PQ. Now if we take the limit as delta t goes to 0, delta r over delta t becomes dr dt. So on top we have a vector dr, but underneath we have the scalar dt. Now let's consider Cartesian coordinates for vector r. R is the position vector of an object on the curve. Well, we could write it like this. We have x as a function of time and y as a function of time. So these are in general both varying. If we want r at time t plus delta t, we want x at time t plus delta t and y at time t plus delta t. So we've two functions of time here encoded in our vector r. How do we get v of t? Well, we know what we have to do. We have to get r of t plus delta t and subtract r of t. So we have to take this vector here and subtract this. So we just subtract the corresponding components. So we take the I component of this vector and subtract the I component. So we have x at t plus delta t I minus x at t of I. So we can just combine them together. And then we want to subtract the y components. So here we take y at t plus delta t and subtract y at t. Of course the whole lot is divided by delta t. So when we're taking our limit as delta t goes to 0, which is what we have to do, we're just calculating this thing here. We're taking the limit as delta t goes to 0 of this quantity here, which is just a definition of the derivative of function x with respect to time. So getting x at some time t plus delta t minus x at a time delta t earlier divided by delta t, that's just a definition of the derivative. And similarly for this here, we have dy dt. So another notation for the derivative of a function with respect to time is to use a dot over x and a dot over y. We can extend the previous result to the case of a trajectory in 3 dimensions, where we need a third basis vector k to represent the third dimension. So we could apply what we just did to 3 dimensions. We would just have an extra term. We would have z of t times k, and then we would have z of t plus delta t times k here. We'd have an extra term here, and we would have the derivative of z with respect to time. So we would end up with this here. So this is a velocity vector in 3 dimensions. Now the magnitude of the velocity vector gives us the speed of the object. That would be v without a line underneath. It would actually be root x dot squared plus y dot squared plus z dot squared. We just use Pythagoras' theorem to get the magnitude of a vector. Now the acceleration vector can be got in a similar way if we do what we did previously, but instead of r, use vector v and do exactly the same. And we would see that the acceleration is got by differentiating each of these components. So we get x double dot here, y double dot here, and z double dot. Let's take this example here. So here we are dealing with an object moving in 2 dimensions. So vector w represents the position vector of the particle or the object. dw dt will give us the velocity vector, which would be tangential to the trajectory. To get dw dt, we just differentiate each component with respect to time. So we differentiate 3t squared to get 6t. The derivative of the cos function is minus sine. Using the chain rule, we have a 2, so we get minus 2 sine 2t. If we want the magnitude of the velocity vector, we use Pythagoras' theorem. We just square each component, sum them, and take the square root. So the magnitude of the velocity vector is the speed. So this will be a positive quantity. The speed is always positive. Finally, we want the acceleration vector. Well, that's the second derivative of the position vector with respect to time, or the first derivative of the velocity vector. So we just differentiate 6t with respect to time to get 6. Differentiating sine gives us cos, and then by the chain rule we have a factor 2 here. 2 by minus 2 gives us minus 4. Now you can also prove that the derivative of a sum of vectors is the sum of the derivatives. If we differentiate a scalar times a vector, we can use the product rule. Now the scalar c could be a function of time. It's not a vector, but it could be changing with time. So if we use the rule for differentiating from first principles, just get cw at t, then get c times w at a later time, which would be t plus delta t, and run through the first principles derivation, you will get this result here, which is what you'd expect for the product rule of 2 functions, except that in this case one of the functions is a scalar function and the other one, w, is a vector function. So what I'm trying to say is that we have to take this limit here if we were going to get this derivative from first principles. So our function is c times vector w, so we need to get c times vector w at a time t plus delta t, and then subtract cw at time t and divide by the difference in the times, which is delta t, and then take the limit as delta t goes to 0. So I'll just maybe quickly kind of run through this. What we have to do is just add in these 2 terms here, c at t plus delta t times omega at t, and just subtract it off then, of course, because we can't just add it in. We can do some arranging then. We can take c at t plus delta t out, and then we have W or omega at t plus delta t minus omega at t here. So you can see where this is leading, and that's these two terms dealt with, and then what we're left with then can involve taking omega out. So we've c at t plus delta t minus c at t. That's from this term and this term, and the whole lot is divided by delta t, so I can just stick the delta t in here and I can stick it in here. Now if we take the limit as delta t goes to 0, well, this quantity here is just going to go to the derivative of vector w with respect to time, and this quantity here is going to go to the derivative of the scalar function c with respect to time. So anyway, this is the kind of thing that we use to prove the product rule for a product of two scalar functions, but it also works here. You can also prove that that if we have the dot product of two vector functions, the derivative follows the same form as for the product rule for the product of two scalar functions, and similarly for the scalar product of two vector functions. So rather than proving those results, we will just verify them for some specific cases. So let's verify the dot product of two scalar functions of time. We want to take the derivative of the dot product, of two vector functions. So by the product rule we should get this. So let's just do that. Let's first of all take the dot product of these two functions. Well, we just multiply the I components together. That's 3t by 2t squared, that's 6t cubed. Then we multiply the j components, minus t squared by 3, and we get this scalar. So the dot product of two vectors gives us a scalar. Now let's take the derivative of it with respect to time. Well, that's easy. So that's the left hand side here. Now let's look at the right hand side. We need dz dt and dw dt. Well, dw dt is 3 minus 2t, or 3i minus 2tj. So differentiate each component. Then dz dt, differentiating each component gives us 4t for the I component. And when we differentiate 3 we get 0. So, you know, these derivatives are of course vectors. They're not scalars. Next we calculate this quantity here. So we want a dot product of w and dz dt. Well, here's w. We want to dot it with dz dt, which is 4ti. So we multiply the I components. That's 3t by 4t. That gives us 12t squared. Then we have minus t squared by 0. We 0 j component here. That gives us 0. Then we have vector z, which is 2t squared I plus 3j, dotted with dw dt. So we multiply the I components together and then the j components together. And we do indeed end up getting 18t squared minus 6t. So this rule is true, at least for this particular example. And in fact it's true for all cases. Let's take this example here. We're interested in the cross product or scalar product of w with z. So to do the left hand side we first of all have to get w cross z. Well, we can do it this way using this determinant. The first row is I, j, k basis vectors. The second row is the components of vector w. The I component is 3t, the j component is minus t squared, the z component is 0, and the third row involves the components of vector z, 2t squared, 3 and 0. Now to evaluate this determinant we can use the third column because there's only one entry in it. So we look at this entry here, k, cross off row and column and take the determinant of this 2 by 2 matrix that's left as 3t by 3 minus t squared by 2t squared. So that's going to give us 9t plus 2t to the power of 4 multiplied by k. And that's a positive entry. So the first entry is positive, next is negative, this is positive. And that's the answer because the other entries will give us 0 for this column when we're taking the determinant. Next we get the derivative, so we have to differentiate this with respect to t. So we get 9 plus 8t cubed times vector k. Okay, so that's the left hand side. Now as for the right hand side, we want to get w crossed with dz dt. So the second row here is vector w, the components of w, and the third row involves the components of dz dt. And where is dz dt? Well, we have to differentiate this with respect to t, and we know that that will give us just 4ti. We have no j or no k components. So to evaluate this determinant, we can take the third column. So we have plus vector k times the determinant of this 2 by 2 matrix. 3t by 0 minus t squared by 4t. That's plus 4t cubed times k. Finally, we have w dt crossed with z. So we need to get vector dw dt. Well, that's going to be 3i minus 2tj. So that's the second row here. And the third row is vector z. And vector z is 2t squared I plus 3j. That goes in here. Again, take the third column to calculate this determinant. We have plus k times the determinant of 3 minus 2t squared 3. That's going to give us 9 minus 4t cubed, or 9 plus 4t cubed by k. Now if we add these two together, we get 9 plus 8t cubed k.